So thank you, Jeff, for introduce anti-schema thing. So now let me introduce the name tree schema with a specific code example. So the problem with application development in NDN is because we have to handle the interest and packet level logic. For example, if you have some fancy idea, you need to first write it in the application logic, and then you translate your application logic to the interest and packet exchanges. And actually, we need a systematic way to handle this kind of thing. So to provide a less painful start, we have developed the Python NDN library, which is an NDN client library written in Python, high-level language. And also, we developed the name tree schema. So which we uses the CL's concept, but we use a different design because CL generally uses the dynamic namespace, but in name tree schema, we want to have the static schema at the beginning. So our goal is we want the structure of the application namespace schema equals the structure of the program code. Because every NDN application needs to design the application namespace. So our goal is after you design the application namespace, you have designed your program structure. So now all you need is find the proper components to fill into this namespace and fill in your code. So since talk is cheap, let me show you a code example, which is a proof of concept implementation in Python NDN. So our scenario is very simple. We assume that the user Alice wants to share some file between her computers. So now she has the file in her PC1, and she wants to share it to PC2 and PC3. So she can use her key as the trust anchor, because all computers are owned by Alice. So we want to simplify this scenario for our implementation. So this may be not true for real world, but we just use it. And the file may be large, so segmentation is needed. One protocol we can choose is the RDR protocol. So RDR handles the version discovery and segmentation. Again, in real world, probably we do not need to use RDR, but for this specific demo, let's use it. So we want to use the RDR component as a black box. So let me omit all the details of RDR. So all we need to know now is RDR will generate a metadata packet that contains the latest version number, and this content segmented. That's all. So the overall design is like this. So first, we need to pre-share the Alice key on every computer so they can verify the signature of packets. And then programs runs on the first PC of Alice, and it loads the file into a memory. And then the program runs on the second PC, and it sends interest to the first PC to fetch this file, and the first PC provides this file. So the file is cached in the memory of the second PC. And then the third PC runs the programmer, and it sends out the interest to fetch its file. And since the second PC has already fetched this file, so it's able to provide this file. So now the second PC serves it, and it's cached in the third PC's memory. So what about the namespace? In this specific application, we have only two objects. The first is the file that's going to be shared. So we just name it /file/file name. Here, whatever in the bracket is a pattern variable, which means that it matches exactly with one name component, but we don't know what name component it is at the design time. So at the runtime, the user will provide a real file name, like foo.txt. If so, then the real name will be /file/foo.txt. And since it's handled by RDR, so we use RDR node here. We just put it as a leaf node, and that's all. We use it as a black box. And the second object is Alice key and certificate. So a real name would be /alice/key/real ID/self/real certificate ID. But at the design time, we do not want to hard code all these things into the program. So we use pattern variables. that is /id name /key /key ID /self /certificate ID. And here we use a normal node because it can fit into one data packet. So let's put this into code. So first we have a root node, and then we have a node at certificate ID, and we have the RDR node for the file name, and that's it. Now let's talk about the policies. So besides the namespace, we have decided several things. One is that we want the program to cache every data packet in the memory. So whenever the PC3 wants to fetch this data, the PC2, who has already fetched this data, can serve it from its memory. And second is we want to verify that this file is signed by Alice key, not something else. And the Alice key should be preloaded and stored in memory. And actually, this certificate can be put into the memory cache before the program runs, so it shares the same storage with the file object. So now let's write these two policies. So first, we need to get the default identity name, because we need to verify that this object is signed by Alice. So ID name would be Alice in this case, and we create a memory cache, and then we set the cache policy to the root, which means that all data packets under this subtree will be put into this memory cache we created. And then we set the policy of the file name. So it's a data validator, which means it will validate every data packet's signature and discard all data packet that does not sign properly. So the policy is it should be signed by the /id name /key /key ID. So signed by this node. And we require that the ID name equals to the ID name we provide, which means this ID name must be Alice. So we are almost done here. So the else things should be first, we need to store the certificate into the memory. So it does not send the ingest packet to fetch the trust anchor from online. So we just get the default certificate and put it into a cache. And then we attach the tree to the phase. So here we attach it to the NDN app. The NDN app is a phase concept in Python NDN. And since the program can be run as both a producer and the consumer. So if it is a producer, we need to produce the file. So we should call the produce function of this RDR node. However, when we want to produce this file, we cannot call /file name dot provide, because we need some real name when we handle real data packets, like what we do in CNL. We cannot use this pattern variable. So here what we do is we call match function. So we match this tree with a name, that is /file plus the real file name. It may be foo.txt. So after that, so the tree will match this pattern with the name. So first the component is file, so it matches file, and second component is /foo.txt, so it matches the file name with foo.txt. And now we have the real name. We can call the provide function and put the data there and some necessary metadata parameters, just like what we do in CNL. And if it runs as a consumer, we can require this file. Again, we just call await root.match, and we put the real name here, that is /file name, and we call the need function. So that's all for code. Let me show you a demo. So first, let's start the first node on my computer, and we set the name to be temp, and the file is copy. And then we start the second node, and to fetch the file from the first node. So now the file is fetched to the second node, and now let me shut down the first node. So and start the third node. So the third node will fetch the file from the memory cache of the second node. So here we only specify tab, so it would be run as a consumer, and we can see that the file is fetched to the third node. And the third node is serving the failed attempt now. But how does this thing works? So actually, our namespace schema looks like the tree in the left-hand side. So we use RDR node as a black box, but actually RDR node is composed with two nodes. One is the metadata data packet, which contains the latest version number of this file. And the second part is a segmented node, which handles the segmentation of this content. So a segmented node contains another node which has a segment number pattern. So it handles segmentation. And on the right-hand side, I show you the runtime name tree, which is used in the CNL. So for example, if we use key as /alice/key/29, and the file is /file/full.txt, so we will have 4 data packets here. So one is a certificate, and we will have a /file/full.txt/metadata, which contains the version number. We assume it's 1600. And if it has 2 segmentations, then we will have 2 segmentation data packet, which has the name /full.txt/v equals to 1600 and /segmentation number equals to 0 and 1. So when we call the match with match/file/full.txt, the producer, the schema tree will go these paths, and it matches with the RDR node. So we call the provide function of the RDR node. So the RDR node is some components that has already been implemented in the library. So it will call the provide function of this metadata to generate a metadata number, to generate the version number. And then it calls the segmented nodes provide and puts the content there. The segmented node will call the provide function of the actual data packet. So the segmented node handles the data segmentation, and RDR node handles the versioning, and it uses the segmented node. And our program uses RDR node. And when the consumer consumes this file, is similar. We just use match/file/full.txt. So it's go to RDR node, and we call RDR node's need function. So RDR node will first call the metadata's need to get the version number, and then call the segmented nodes of need. Here, when a packet flows to the RDR flows to the leaf node, so it will see that there is a signed by policy assigned to this subtree. So the schema tree will first check its signature against this policy, which points to here. So it will see that this data packet is signed by /alice/key/29, which matches this pattern /name/key/29. And it checks that the ID name equals to Alice. So this policy is satisfied, and it returns the data packet to the segmented node and the RDR node. And every data packet will also be stored in the memory because there is a memory cache policy. So as a summary, our goal is we want the application's namespace equal to the code structure. And we want to have a application framework that all different NDN libraries can be integrated into this library. So we have 2 things here. One is the custom node, just as the RDR node and the segmented node, which are actually substructures of namespace or subtrees. And the second part is the policies, which acts as filters or some annotations attached to this tree. So the tutorial with the code is online. Here is documentation of the Python NDN. And our future work includes the sync, because sync is a core part of a CNL, and we want to include the function of CNL. And we may include the repo. So we can use in-network storage instead of memory cache. And then we may want to serialize this schema tree, like we use XML or something like that. So other networking parts like NDN routers can recognize this application data application namespace. So that's all for my talk.
Okay, thanks. So we have time to take a couple of questions. There's one question from Slack. It says, in the example of 3 computers, how does the second and third PCs know when to send interest for the file? Either sync in the background to let the 2 consumers know when the new data available, or is there any other mechanism?
No, actually, sync has not been implemented in this NT-schema proof of concept demo. So what we do is when we run the second program manually, so it will try to fetch its file and send the interest.
Okay, so in the real application, it will have to implement its own mechanism to decide when to send interest.
We are going to implement sync in the future.
Okay.
But let me just inject here just a bit. I think I just typed in the reply in the chat in the Slack. I think it's in the question depends on the bigger context where this file sharing happens. If it's entirely isolated incidents, that is, oh, okay, out of a blue, one wants to share files, then you need some mechanism to invoke other people, other components to fetch the file. But if the file sharing happens in a context for other application, I use the example of a chat. Very often in the Zoom chat, we share files. So therefore, the notion that, oh, people are sharing a file is already embedded in this bigger context. So therefore, every node knows there's not only the file to share, but they also learned from the chat what the file name is. So they can send the proper interest package to fetch the file. So therefore, I do not think there's one specific answer. It's really depends on the context. And the second, and actually I want to emphasize, I think Xinyu gave a specific example of how to utilize the name tree to drive the application development. This talk is not meant to address this broader issues of how you learn even there's a file to share. Actually, there could be other driving examples, but I think you pick the simplest one, just to make the explanation easier to grasp. I'm done.
Yeah, what I want to emphasize here is this demo is only shown to be a proof of concept demo. So I want to show that the application structure can be the same as the application's namespace schema. So I didn't mean to show a real world scenario to specify that we should do this when we want to share a file.